Just gonna check my email and we'll give people a few minutes just to join. So a bunch of students have emailed me questions, so I have them written down. But anyone in the audience, if you have a question at any time, feel free to unmute yourself and ask it, or you can message me and I'd be more than happy to answer it or ask it during the panel. So with that, I'll start off with at least the first question. Can our panelists please introduce yourself, state where you work, and can you emphasize your role in IFE? Matt, why don't we start with you?
All right. Hello, I'm Matt Wolford. I'm at the Naval Research Lab. My title is I am the head of the section of electron beam science and applications, which really means that I'm in using electron beams to develop lasers. That's what I've done in the past. So my role in IFE is trying to figure out the critical technologies to help the driver to be successful to run at rep rate, low cost, high efficiency, and those types of issues for IFE.
Don't forget about long lifetime.
Yes, in long lifetime. Thank you, Allison. You're absolutely right.
And with that, Allison, why don't you take over next?
So I'm Allison Christopherson. I work at Xcimer Energy. We're an inertial fusion energy startup company, and my title is head of target design. So my team is mainly a coalition of a lot of external partners, including General Atomics, who makes the targets themselves, or they will tell us if what we're doing is not possible. But the job is to set the target and laser and target injector specifications to come up with designs that can produce fusion gain and are compatible with our system level goal of an FPP. So this involves interfacing with the laser, chamber engineering, diagnostics, target fab, everybody.
And with that, Neil?
So I'm Neil Alexander. I work at General Atomics. I'm the director of inertial fusion energy, which means I look after our programs we have, both external and internal, that are related to inertial fusion energy. That's mostly related to how to make targets at high rep rates and affordable costs, which isn't available today, and target injectors and tracking the flight of targets and how to hit them on the fly. So I'm part, I lead the additive manufacturing for targets within the Starfire IFE hub, and to try and make foam capsules via microencapsulation within the RISE IFE-STAR hub. And then we were awarded one of the FIRE collaborations to develop a target injector and tracking systems and put that on the ALIF lasers at Colorado State. So that'll be a team of Livermore, SLAC, Colorado State, UCSD, and ourselves. And that's a good place to start.
Yeah. Thank you guys for your introductions. So just more of like a general question. Where can students learn more about your role in IFE or, what are some good resources that you can recommend for anyone that wants to dive deeper into the areas that you work in? And if you have any specific review papers or whatnot that you recommend, you can always send them to me and I can forward it out to everyone later.
All right. I guess I'll give a suggestion. If I was a student and I would want to learn, I would try to look at some place, not just a review paper, but maybe try to I'm into pictures, okay? So I like presentations. So one of the places I would look would be a website called qedfusion.org/HAPL, HAPL. and it has all the presentations from the HAPL program between 2001 to 2009, which was a laser IFE program that I know Neil Alexander was a part of. And it at least gives you an idea, because we have mostly laser people here looking at it right now, of how a laser driver and the various components of what's going to be required for an IFE power plant, with some detail and a lot of different types of pictures and ways to look at. That's my suggestion.
Thanks, Matt.
So general resources, there's a few review papers I would recommend for direct and indirect drive, and I can send you the links. One was written by Steve Craxton, who had a very long career at the University of Rochester in direct drive. And there's two main laser-driven fusion facilities in the United States. One is in Rochester and the other one is NIF. But yes, the review by Steve Craxton highlights a lot of the contributions to direct drive laser fusion and a review of also implosion hydrodynamics. And then for indirect drive, the review papers by John Lindell that document a lot of what was learned in early Livermore ICF facilities like NOVA, and the campaigns on the NIF are really good resources. So, and John Little was the chief scientist of Livermore's program, and Omar Hurricane also has some papers about the last 10 years of the fusion program, who's the current chief scientist. So you're learning it directly from the source.
Thanks,
And if you
Allison.
want to learn about the expertise, then I would recommend Rochester as a place where that's where you go to learn about implosion hydrodynamics.
So I have a few things one could look at. So in 2023, there was an IFE community workshop, which I think Livermore hosted virtually. And there's a lot of white papers on there. So you can get like who's interested in what and what they're doing from looking at those white papers that are collected on that website at Livermore. And that fed into an OFES IFE Basic Research Needs Report. And so that's a good way to look at it. Several people in the US helped Germany put together a memo on inertial fusion energy to help convince Germany that inertial fusion energy was worth pursuing. So that document is available online. Livermore has a lot of the life design articles online. And then if you're interested in more of like the history and how people have thought about this over the years, the University of Wisconsin has a web page that lists not just magnetic fusion energy reactor studies, but inertial fusion energy reactor studies. You can get links to past efforts like Sombrero and Cyrus and Sirius, Highball. So there's actually been quite a few reactor studies over the last 50 years. And I think there's also sort of an electronic encyclopedia entry. I forget which one that I'll try and find it that has generic overviews of IFE.
Thanks, Neil. So the next question, what was your journey to get to where you are today? You know, what made you decide to tackle IFE, and why are you still working on this problem? Whoever
All
wants to
right.
go
I guess
first.
I'll go first again. I don't need to go first. So my journey's probably a unique one. I was always interested in energy and power as a kid, but I chose to pursue chemistry, and I was a physical chemist. I got my PhD at the University of Pennsylvania in ultrafast chemistry. We used the laser to basically to do chemical experiments and in ultra fast. I had no background in plasma physics, no background in fusion, and but I knew how a little bit about how to build different kinds of lasers. And I I put at the time I put my resume on something called monster.com, and I got called by a contractor for the Naval Research Lab that told me about a program that was being generated at the Naval Research Lab in regard to electron beam pumped lasers. I knew nothing about electron beams. I know nothing about plasma physics. I really don't know much about either one of those things to this day, even though I'm in a plasma physics division and my title says I'm electron beam science and applications. You learn various tools. It's your skill set as a scientist is quite wide ranging, and I'm a big believer that if you think you can do something, go ahead and try it and fail again and fail again, and eventually you'll overcome. That's kind of my philosophy of IFE and why I'm in IFE is because I've enjoyed failing. I enjoy trying to make a little bit of accomplishments, make small movements, and it seems like a worthwhile pursuit, and that's what I enjoy the most.
Thanks.
Yeah, thank you for that, Matt. I'll go next. So how I got involved. So I think as a kid, I really enjoyed physics, and I used to like wonder like what is a molecule and what is an atom and what is a neutron and a proton and what exactly is mass? And you can easily go through the cosmic onion and drive yourself insane, right? If you try to keep taking it to the logical conclusion. But I was fascinated by physics, but I didn't know any adults around me who were involved in STEM, so I had no concept of what a career would even look like in science. So when I went to college, I enrolled in engineering. I think I was just naive. I just enrolled in engineering because I didn't think physics was a real career path. That was just ignorance, but I chose nuclear engineering because they let me take the most physics classes. And at some point in my sophomore year, I learned about the NIF, and I learned that there are people who get paid money to blow things up with lasers and see what happens. And I thought, wow, that sounds pretty cool. And it was not driven by duty, right? It was just, wow, there's people who get paid to do this. So I ended up doing research in plasma physics, and I really enjoyed open and unstructured problems, right? So instead of working on a designated homework assignment that a professor gave to me, I enjoyed deciding what I wanted to learn and work on. And so I knew I wanted to do research. And when I wanted to do inertial confinement fusion, University of Rochester was the logical place to do it because they have a facility. It has the purpose of training students. So I did my PhD there. Then I went to Livermore for about 3 years, and I was at Livermore during the time when ignition happened. And after ignition happened, everybody is thinking about, well, what's next? And at the time, I was not a believer in IFE because I didn't, even though NIF got to ignition, there were so many technical challenges that the implosion had to overcome that I could not see how you could have a target that's injected and aligned with a laser, and that gives you robustly high gains and is stable. But then a mentor connected me to a couple of guys who are living in Foster City with their dog, right? And they invited me over to play Battlestar Galactica, which is how it started. And eventually they formed a company called Xcimer, and they have a solution to build a laser that can scale to 10 megajoules and lower cost. So I thought, wow, this is something that really overcomes a limitation that I thought was otherwise not possible. So then I got involved, and now I'm at a startup where I'm responsible for leading a program. So I'm making the transition from an individual contributor to a program leader, which involves making lots of mistakes and correcting them and making more mistakes and correcting them. But it's exciting because now instead of focusing on one narrow role of interpreting this one experiment, now I get to have a broad exposure to everything. So how everything affects the target design in optics, lasers, chamber, nuclear engineering. And now I'm more involved in target fab. So I find that exciting, but I hope that answers your question.
Yeah, it's a fun journey to hear. And Neil?
Yeah, so like in high school, I remember having the high school physics course had sort of a abstract version of a tokamak on the cover and sort of a cover thing that says, oh, we can, do fusion like the stars. And then I did physics and chemistry as an undergrad, and I thought I wanted to do gravity, general relativity type stuff. So I went to one of the schools that had a lot of that. But after a couple of years, I found, oh, I really miss building things. Like I've always built things, uh, sort of as a hobby basis, as a throughout my youth and even to this day. But I found I really missed that. So then I looked around. Well, where I'm in grad school here, who else is doing stuff where I can be in an experimental program? And I found someone who was developing spin polarized fusion fuels. And so I ended up in his research program trying to develop a way to polarize the deuterons in solid HD and be able to transport them in a target to the old 24 beam omega. I did a lot of development on this was in dilution refrigerators, how to get the sample up to 4 Kelvin and transport it, an hour's drive down the thruway from Syracuse to Rochester. And that sort of led to my first job where they're like, okay, we're upgrading from 24 beams to 60 at LLE. We need a new cryo target system. They asked GA, which had just gotten the target fab contract from NNSA, to help with that. And they said, hey, there's this guy who just graduated. Why don't you, who has experience with cryogenics, why don't you have him help you? So that got me to GA. And then it's been Mego cryo system, NIF cryo system. Then there was this HAPL program that Matt mentioned that I was in, and it's been on ever since for me.
Thank you. That's also just a very fun journey. That drive from Rochester to Syracuse must have been fun. Um,
Not in the winter.
yeah. So how can students learn about opportunities at your company, whether it's looking for an internship or co-op or a postdoc position or, full-time position, let's say they're close to finishing. And do you foresee any openings in the next year? What would be a good time to apply? Things like that. I know funding is very challenging right now, so it might not be an opportunity in the moment.
Um, our website is the best place to look. At the moment, our funding is very tied up until we raise our next round, but I expect our opportunities will be more available in about a year from now.
I
But
guess
yeah, our website, yeah.
I guess I'll go next. So the Naval Research Lab is a federal entity, and because we're a federal entity, we're the place to go would be USA.gov or USAjobs.gov, and that's the website for federal jobs. But if I were to look for a job with the federal government, like the Naval Research Lab, I would contact directly with someone's staff that of scientists that I would find that it's interesting of what I would want to pursue and see what their funding profile and see what the opportunities they could lead me down for postdocs or positions. And then the second part is in terms of hiring, then Naval Research Lab is a federal employee. And if you watch the news, you probably have an idea that we're under a freeze in hiring right now. And that will go on for some time. I imagine we don't know when it will end. But at some point, we've had a lot of departures. And if the facility is going to be maintained, we're going to have to hire a lot of people as soon as the conditions allow us to hire again because across the whole laboratory in a lot of different sectors. Um, we've lost a lot of employees recently.
I would say, again, we have a jobs posting at General Atomics, and you can go in there and filter on the inertial fusion or other keywords like that. Um, but again, trying to find, like Matt said, who's doing the work you're interested in. So looking at publications that come out of General Atomics and seeing who are the authors and then trying to get in contact with them to see what's going on. So maybe through LinkedIn, or there may be email addresses in the article, just like contact them and say, you know, maybe not just who, do you have positions or do you know of anybody who might, to make it a little broader ask. LinkedIn might be another way to get in touch with people. Um, we've had a lot of budget reductions, so the whole, a lot of us are funded through the federal government, and we'll just have to see when that uh, funding becomes stable again. We'll see.
So it seems like the takeaway is if you see enough, or if you are interested, to reach out to someone directly, maybe within the next few years after funding becomes more available. I think that would be a good summary. Just want to remind the audience, if you have any questions at any time, you are welcome to unmute yourself, or you can message me and I'd be happy to ask your questions. So with that, I'll start off with another question that was sent. So, what is, some skills that you would encourage students to work on while, during their studies to make them possibly better applicants, whether it's in your company or just in the field in general? I know one of my PIs, he always emphasized learn LabVIEW. We always did experiments, so that was one skill that he suggested.
I can go first. So it does depend on the function, of course. I myself, I am a theorist. So for students who are interested in theory and computation, one thing I do recommend is cross-domain fluency. So it's not enough to just be good at theory and computation. It's also important to be able to interface with the experiment. So it doesn't mean that you have to know every single detail about a diagnostic, but when you're coming up with a theory and testing it in experiments, you need to interface with the experimentalists and understand what data you're looking at and what are the limitations. And likewise, if you're an experimentalist, then working with theorists to understand the limitations of the models that they're proposing and how that can affect the data is also important, right? And even in computation, it's not enough to just simulate plasmas. I think even if it's a simplistic model, taking the time to mathematically go through the analytical models to understand your system is very valuable. And I think it's becoming a lost skill sometimes. So I also encourage students to not lose track of theory work just because it keeps you in touch with the physics, even as you want to move forward with these tools like AI and computational physics, etc. Yeah, and as you mature in your career, as much as you can, cross-domain fluency. So even in my role right now, it's not enough for me to just know about the target design. I have to understand the constraints on the architecture of the laser system itself. And this is a very close feedback relationship, right? So the laser scientists have to learn more about the target design to understand how they can produce a system that meets our needs. And likewise, I also have to be flexible to think about their constraints and how I can redesign things to meet it. So, yeah.
I'd agree and sort of one first, where am I coming from? Like we're suppliers mostly of things like targets or target fielding equipment. We do have a few people who are doing experiments, but we are primarily producing things. So broad skills in like designing and building apparatus or running chemical processes, CAD. And then there's this whole separate thing of scheduling and writing. A lot of our deliverables are writing reports, having good writing skills. And we got to get money. So learning how to do proposals, that was something that was very lacking in my education throughout grad school was I left grad school with no idea how to write a proposal. So bug your advisor on how that's done, I guess.
I think they would gladly accept help on any proposals.
Once worth, Neil, I love your reports.
So and like, general, like all these aids on computer aided design or whatever, it's like CAD or running an FEA code like ANSYS or an Neutronics code like OpenMC or MCNP or a PIC code or a fifth generation or fourth generation language like MATLAB, just like the ability, or Python, just the ability to get computers working for you to do what needs to be done. My suggestions.
I agree with everything Allison and Neil said are very good suggestions, and I would probably emphasize Allison's cross domain is probably what I would say is the most important thing is the willingness to learn various aspects of how things interact with around you. And definitely agree with Neil that writing proposals was something that I also lacked in my experience, and I've been forced to do a lot more writing than I ever really wanted to. Um, but one thing in regard to both those things that I found very beneficial, if I was a student today and looking back on it, is I would spend some time reading the literature of my topic. So one, it does two things. One, it spend the time to know, so I'm not reinventing the wheel. I know people have already done it. I know what's been done. I have a command of that. But also, if you do a lot of reading in the library, you'll learn the communication skills of how people presented things in the past. And reading over and over again, you'll learn phrases in the way to phrase things successfully in a scientific audience. And I found that to be very helpful for me uh, to learn about by reading literature over of what was done in the previously to my entering. And I still do a lot of reading of what was done by colleagues and stuff to try to understand what, in regard to what, like Allison said, cross-platform. I try to read as much as I can read. That's what I think is helpful.
And Stefano, do you have a question that you would like to ask?
Yeah, just briefly on the code side of stuff. So, as sort of someone coming into the simulation side of things, are there specific codes that you're seeing are kind of more commonly used in industry that you'd recommend incoming students to pursue or sort of become acquainted with?
That's a great question. Yes, but it really depends on the context of the problem you're solving. So I guess I would say think about the problem you want to solve first, and then work down for which tool is the most appropriate. So, like in plasma physics, a commonly available code is Flash for simulating laser plasma interactions, right? Well, it's a hydrodynamic code, but that depends on the scope of what you're trying to do. And if you want to work at a national lab, then they do have important codes and tools to use for fusion modeling, but they're often export control and limited. So it's not like you can just access them whenever you want. So yeah, my recommendation is to focus on the problem you're trying to solve first, and then work down on what is the right tool to do the job.
Thanks.
And Neil and Matt, do you guys have anything you want to add?
Allison's the expert.
Yeah.
I'll just say, like in engineering type stuff, Or, you know, we use GA uses a lot of ANSYS products. And a lot of the design work is done in SolidWorks.
And Allison, correct me if I'm wrong. I believe Austin, who does your kinetics design, he uses Python, if I'm correct, for looking at that.
Oh yeah, so I mean Python is just a general purpose, right? So Python, I would say across many scientific and engineering domains, it's just a general purpose language that you can use for a wide variety of problems and scripts. And yeah, there is a difference between high performance computing and just general daily purpose, right, work and calculations that you're doing. So Python is something that I think most scientists use it routinely. It has a lot of excellent modules and options to accelerate your work. And if you use ChatGPT a lot, then tasks that used to take me an entire day now take me like less than an hour, right? Which is great. Um, I personally still use Mathematica sometimes to solve equations because I like their ODE solver, but yeah.
I use MATLAB for
Austin's
laser rate
typing.
equations.
Yeah, a lot of people still use MATLAB, so MATLAB is not by any means extinct.
You know, I mean, we sort of have standard access to that and Python. I like a very old school program, so I won't mention it, but
Neil, my husband uses Fortran, so
As a grad student, I had to use Fortran.
yeah.
So,
Well, thank you, Stefano, for that question. And just for our panel, Stefano is currently at Slack right now. Are
Can
there
I
any questions?
ask a question?
Yeah,
Yeah.
please go ahead, Richard.
Okay, so the Richard Sandberg from BYU, and I'm currently at Slack running an experiment with a lot of the students. So sorry that some of them aren't available. And you may have touched on this a little bit earlier, but do you have opportunities for undergraduate internships at any of your companies?
yes, yep, we do. We take undergrads and grad students.
Where's the best way to learn about that? Just at your company's websites or contacting you individually?
Yeah, the website is the best part because you can directly apply, and we have a head of talent who oversees all of the applications and will go through resumes. Contacting people on LinkedIn is also helpful. So I normally, when we take on interns, there's a few ways it comes up. Sometimes it's people I've met at recruiting events. Sometimes our head of talent will filter through resumes and pick out the ones he thinks are a good fit for roles. Some of them have been through like word of mouth, right? So I have a professor who consults with me at the University of Michigan, and he had students who wanted to get involved in our project together. So that was also one way to facilitate it. But for general purpose, I would recommend the website, or we can go through the CSU Hub, and that's another avenue, right?
Yeah, that's a great idea.
yeah. So we have sort of 10 to 20 undergraduates, depending on whether it's during the year or the summer in all of IFT. In IFE, we might have 3 to 4. One way it's possible to do it is through the DOE's SULI program, Summer Undergraduate Laboratory Experience, or something like that. But basically, lots of the companies and DOE labs that have opportunities kind of put in suggested projects, and then the students who get selected for SULI kind of look through all the projects and say, oh, I want that one. And there'll usually be several from General Atomics, both in IFE and in ICF and magnetic fusion energy. So that's sort of like a separate way, which is separately funded to do undergraduate internships at various places, including GA. Otherwise, it's kind of like looking out for what's on the website, but it's good to try and be in contact through LinkedIn or, email to just say you're interested, and basically for someone like me to be able to say, "Oh, I have created that job posting and please apply." Because sometimes, they're they're easy to miss, is I guess what I would say. So if you have sort of a first alert from having contacted someone by email or LinkedIn, and they think you're a fit for what they want, then you at least
Thank,
have a better chance of finding those job postings.
yeah, thank you. Thank you, Neil. Yeah,
Well,
I've had some experience with Suli, but often the potential advisors need to be looking and pulling from their end, right? Or they don't get paired up with the right advisors. Matt,
yeah, I was just going to say at the Naval Research Lab, we have a lot of opportunities on our website called www.nrl.navy.mil. There's a tab called opportunities. Uh there's quite a few high school programs that we do have where we have either assistance or various ways that either the research advisor, we're a working capital fund, may not have to pay for your time in our laboratory. We have, and there's a lot of different sets of programs. And so I would reach out directly to the researcher that you'd want to work with, or try to look at the website of what NRL is doing and try to talk to that division or that aspect. And then the people that you're in contact with you will guide you to the appropriate suggested program. You're welcome to always apply to any of the programs here at NRL for undergraduate students. And it goes through each one goes through a different process, and and we do have quite a few students that do come to our institution.
thank you. Very helpful.
So, I guess I'll change gears with this next question. What can we do as like a hub to continue to collaborate with our companies? So, with all of you.
I guess I'll start. So, well, right. I mean, through the Rise Hub, right? Neil is developing these dicyclopentadiene foam targets. So I think the fact that he has space to explore new ideas for fabricating targets, I think that's great. Um, diagnostic development is one area going forward that I believe the hubs can support us through. Uh, Definitely funneling students to get a broad exposure to the IFE community, not just including private companies, of course, but also the different labs and GA, of course. Um, Also, like basics, fundamental science that will help support IFE targets later on. So, for example, a lot of the work that LANL and SLAC are doing right now, I do track it closely. So, yeah, I would say basic HED science, diagnostic support, targets, right, fundamental laser science.
I will say that I think the hubs provide an opportunity to allow interaction. And going back to what Allison said earlier about being a scientist in IFE, the hubs allow you to interact and see every different component that is going to be necessary to have a successful power plant. And it gives that cross pollination feel where you get to learn about what someone else is doing, and then you'll be able to apply that better for the type of area of research that you're doing to make sure it fits into the entire integrated goal of reaching to a fusion power plant. I think is one of the things that the hubs uh, potentially could really help everyone doing, and avoid siloing into just I'm working on this little part of the problem and I understand my part of the problem and the rest of the world's going to have to adapt because this is the only solution I have to my little part of the problem. I think that's one of the things that the hubs allows you to do is allows people to scientists to talk as equals, as partners to try to solve complex problems. And there's a lot of integration problems in building a fusion power plant. That's what I think.
For me, targets, you know, you want to know as much as possible about them, their dimensions, where there's impurities, inclusions, voids, what their dimensions are, how full they are with fuels, and there just isn't time to develop every option for diagnostics on and metrology of targets. So, ideas and activity in that areas would be helpful. And we're doing things like we're providing samples for experiments to try and figure out what is the equation of state when they're compressed of this foam filled with fuel, or how do shock waves propagate through it, or that's more in the end use physics case, but also samples of, there's a diagnostic we have for looking at the chemistry and on a localized basis to see what's in this patch versus what's in that patch. I send out samples for people who have that. So that's another way to get involved. Is what do you know how to measure, and would it help in metrologizing a target? Get samples to people.
Thank you guys. And you all brought up, a bunch of different challenges that you're also trying to pursue. In your perspective, what would you say is the biggest challenge right now in IFE? And I know it's going to change as everyone's in slightly different fields.
Getting things to that long life and reliability and low cost, together as a package, that's the hard part. I see, being able to make a few targets or a laser that lasts for 100,000 shots or something like that. Okay, I imagine those will be possible. Where I see it'll be real difficulties coming is, well, how do I make sure that target costs 50 cents or $1? That the laser lasts for 10 to the 8th or night shots. It's my perspective.
What is the biggest risk? Man, right, there are a lot of technical risks to work through. And it's also, when we're talking about building an IFE power plant, this is arguably the most complicated machine humans have attempted to build. I think you could argue this. So, yeah, the risk I worry about, obviously, because I deal a lot with the target design, is that, in 7 years down the line, we have an ignition scale facility and we start shooting and we get data and it doesn't make sense. And I'm responsible for answering the question of, do we understand what happened? And if not, what do we do next? And with implosions, it's not just about a system that gives you the highest fusion gain, which is already extremely difficult. We now have to find a solution that does that and is also a systems level solution. So something that would be compatible with a target injector. I think trying to ignite with a target injector, I anticipate that will be a wild ride, personally. So that's a big one. And at Xcimer, we're trying to ignite using only 2 laser beams, right? So this is another thing that's very unprecedented, but if we can make it work, this is a solution that leads to a lower cost laser system. So yeah, I think igniting robustly in a way that is compatible with a fusion pilot plant design, that's probably the biggest risk I'm always on my horizon.
I think both Neil and Allison have good points. If I were to pick something, and I might surprise you, I have no knowledge on the topic. So again, I'm going to go with something I don't know anything about. What keeps me up at night is I think we can have a laser. I think we'll have a laser that lasts billions of shots. I think we'll have a laser that engages the target and we'll have gain. I think, and our I worry about is the chamber wall and the blanket, making the tritium, making the fuel cycle, but the wall is the thing I worry about. That's I've been worried about that for a long time because we don't really have 14 MeV neutron sources that are pulsed at, and we don't have any idea scientifically how things are going to work for billions of shots pulsed of 14 MeV neutrons. So it's like a whole new area of science. We have some continuous 14 MeV neutron sources, but that's a challenging topic. And we're going to have to be successful in getting fusion before we really know what the wall situation is going to be. And that's a secondary unknown, and that's I guess what I worry about the most.
So along these lines of, the problems, it takes money to try to solve some of these problems, a lot of funding. If you had unlimited resources, what project would you pursue, whether it's to tackle the problems you just said or some other problem that you're just interested in IFE?
Unlimited resources.
Unlimited resources, think big.
I would immediately start hiring and building the entire team that we need to prepare for an ICF facility, including the design of the chamber, the design and execution of the laser architecture itself. I don't think I would be doing anything different that's not already on our roadmap. It's about developing a program where you have your key risks and you have milestones based off of retiring those risks, and you plan your activities accordingly. And because there's still a lot of science we're working out, you also need to have programs in parallel to investigate alternative technologies. And that's in a startup that is already part of our plan. So I don't think I would do things differently. But yeah, I would also start the target injector and tracking system. That's another one I'm very worried about that. But we'll work on that together, right, Neil?
That's right. I mean, that's what the IFE-FIRE award is supposed to work on. So
Yes.
the money will be come available soon.
And we also have the whole ROM to worry about too. And the mounting structure of the capsule within that whole ROM that has to survive. So yeah, basically we would try to fund everything.
It's like we
Get
like to
started.
say the IFE is a very separable problem. So it's like, okay, start developing a laser module, try the target injection and tracking, work on different ways to make targets, try and develop some facility that can, like Matt was saying, I mean, that what Matt said keeps me up at night too, is like, what's the scheme to protect the wall that the target can survive as well? You know, is there some way we can get to a rep-rated pulse neutron source?
Yeah, that's something I think I have been visualizing a lot the day where we start trying to, in an Xcimer scheme, we're planning on a liquid wall to protect that first wall, but this is a technology that's still very low TRL or technology readiness level. So, right, like what if we turn this thing on and we have all these predictions that the radiation is supposed to be absorbed in the wall in a certain way in this liquid 5 jet. What if we're wrong and we blow up this wall, right?
Get a picture of it or a video at least.
But
Everybody
I'm
call.
sure, but most likely, I'm sure there are much smaller scale steps before you go to that extreme limit, so that if there is a risk, you can address it early before you damage your equipment, right?
You know, the whole tritium recovery, repurification, resupply needs a lot of work. And then where does it really go? I mean, it's like we have this. The other way to think of a IFE power plant is it's really a pulsed laser deposition system. So all this target debris is going everywhere, and some of it'll end up tritiated. Well, where did it go? So can we have a small facility that's just blasting targets that have tritium just to see what happened to that little plasma ball that was filled with tritium? Did it plate out on optics? Did it turn to tar down some plenum? And then are there ways to sort of flush it away with oxygen plasma or something so that the whole system stays clean, doesn't end up clogged up with target debris everywhere?
I guess the only thing I could add, again, my colleagues are spot on. They have great suggestions and things that if they had unlimited funds to spend money on. In regard to lasers, or drivers in general, let's take lasers out of it. Let's just say drivers for IFE. If I had infinite money sources, I would work on solid state switches that last billions of shots. We really could benefit of having switches that last with whatever pulse power, if it's for the pulse power for a dipsel laser or for an Xcimer laser or for a Z-pinch. All these things are going to require the components to last billions and billions of shots that are pulsed, and that's still not in hand. And if I had infinite money, I would do that probably early on, because once you have the driver, then we can work on some of these other problems.
Well, thank you guys for your perspective. And I want to be mindful of your time. Oh, there's one more question. Um, so the last question, which I'll ask, which parallel technologies from disciplines outside of physics are potentially hindering progress of the field?
I'll jump in and I would say, look, we talked about, I just said switches, but we talked about walls and everything. Materials, better materials, better optical materials if you have an optic in your driver, better materials for your wall, better materials for your target, better materials. Materials in general is not, people don't necessarily think it's physics, so I'm going to grab that one first because it's an easy answer. We need better materials.
Yeah. And especially with the magnetic fusion community, that's a very big deal. And with IFE, we believe it's a bad idea to stick a plasma next to a high Z wall, right? That's emitting all of these 14 MeV neutrons. But in IFE, we do have the advantage that we can have standoff, right, with the final optic and the chamber wall. So that gives me hope there's a solution. But you are right, Matt, that the technology readiness level of materials that are on a repetitive basis subject to this radiation, even if it's a small amount in one shot, but when you operate at rep rate, what is the lifetime of these components and how often do you have to replace them? Do you have to shut down the plant to replace them? And the biggest challenge this is true with magnetic fusion. At Xcimer, we're hoping the liquid wall will enable a 20 to 30-year plant lifetime, but a lot of schemes require you to replace the fusion wall every single year, or at least once a year. And that's a huge problem because one, it's expensive to replace the wall. You have to shut down your plant, and this wall is neutron activated. So you can't just take it out. You have to have a proper nuclear waste disposal mechanism in place. So that is one challenge that sometimes is not highlighted as urgent enough as it should be, in my opinion.
So I agree with sort of the materials. There's a sort of a chemical engineering aspect of like how do you make the targets, or the tritium processing and handling, like extracting tritium from the blanket.
Mm.
Another sort of avenue, Allison mentioned the liquid walls, so that's one way to have a rapidly replaced wall. Is you're just spraying liquid down it. But there's sort of and many people are looking for the magic material that's going to last the life of the plant, which I think we're just not going to get there in the near term, like maybe in 50 years, but not in 10 years. And so the intermediate is, can we have robotics for maintenance, or, for switching out things like wall materials? That would be a solution that would enable a lot of different power plant concepts. Is sort of like, how do you handle remote maintenance and replacement in very highly activated scenarios? So, a lot of electronics just dies that one would rely on for maintenance systems. That's another area I think would be fruitful.
Well, thank you. And I want to be mindful of the time. So, first of all, I just want to say thank you so much, Matt, Allison, and Neil, for joining this. Your perspectives were very, very valuable, and I hope that others feel the same way as well. Thank you to everyone who sent in questions. I really appreciate it. It made this session very fun as well. So, with that, I will stop the recording, and I hope everyone has a great rest of their day.